what you can do with this simulation here. So one way to do that is to just talk about all the circuit elements that we have and make some measurements. So let's bring that battery back. There are ways of, with this simulation, of measuring voltage. Voltage on the vertical scale, and time is kind of slowly going by on the horizontal scale there. Voltmeter measures the voltage difference between 2 points, and so what you find is that the voltage difference on a battery is constant. There's something we haven't talked about much yet, call it AC voltage. And you can already see what that is. The AC voltage is changing all the time. It's minimum -10 and a maximum 10. We can look up the frequency, or we can change the frequency by clicking on it. Change the frequency. This is 0.5 hertz, and we can change it to 2 hertz, so it'll go up and down faster. Higher frequencies, shorter period. We'll go back to the 0.5 that it was set at. Just leave it right there for right now. AC source, with respect to Faraday's effect, you know how a generator produces an oscillating EMF, and that's exactly the way that these are ordinarily produced. Other things we can see with this simulation, a resistor. You know, if I hook up a resistor to a battery, then current flows, but if I hook it up to an AC power supply, AC voltage, AC voltage is of course going to be oscillating up and down. The question is, what does the current do? We can monitor not only the voltage, in fact we could monitor the voltage across the resistor. And you see that when the voltage across the resistor is small, like there, the current is low, the voltage is a maximum, the current's a maximum. So these line up. When there's a big voltage, there's a big current. If there's a big voltage, whenever there's a big current, you say that the current and the voltage are in phase with each other. So this in phase right here means, what it means is the voltage has the same sign function that the current does. The sign function part's the same. The part out in front, the amplitudes are of course going to be different because, for one thing, they're different quantities and they have different units. But the time dependence is the same. What about a capacitor? That's another circuit element that we've talked about. I can think about. I can get rid of this resistor. Put it over here with the battery. Bring a capacitor into the problem. Actually, I don't really want to get rid of the resistor. Every circuit has some resistance, so probably I'll just leave it in just to remind you that there is a resistance in every circuit. If I don't put a resistor in, then the wires make up the resistance, or have the resistance, and they would have a very low resistance, so I don't really want to do that on a resistance where I know where it is. So what happens? Current flows, of course. When the electrons are pushed this way, the right plate becomes negatively charged. When they're pulled the other way, the right plate becomes positively charged. So this AC source pushes electrons onto the plate and then pulls them back off again and pushes them onto the other plate, and then back, and then back, and then back. And we can monitor the voltage difference across the capacitor and the current. And we know something about the voltage difference across the capacitor. It depends on the charge. The funny thing about the charge is that the current depends on the time rate of change of the charge on the capacitor. So the current, if it depends on the time rate of change of the charge, Q, then it depends on the time rate of change of the voltage across the capacitor. So suppose this voltage across the capacitor was a sine wave. So that's what we're measuring here, is this sine voltage. Across the capacitor, the current is a time derivative of that. Time derivative of a sine function is a cosine function, and that's just a sine function shifted by pi over 2, by a quarter of a period. So the current is not a maximum when the voltage is a maximum. Here's the voltage down here. The voltage is a maximum, it's a minimum. Voltage is a maximum at about 494. If I look over at 494, voltage, the current is 0 at 494. You can see why that happens. Why would the current be 0 when the voltage is a maximum? Well, the voltage is a maximum when this thing is fully charged. The charge is as big as it's going to get when the derivative is 0 at the maximum. So that's the sense in which the current actually leads the voltage in a capacitor, because they aren't maximum and minimum at the same time because of that derivative back here. I can put an inductor in place of the capacitor. Look at the inductor voltages. Still going up and down 10 volts. Let's go back to some reasonable frequency so we can see the peaks, see where the peaks are a little better. Back around that kind of frequency, then we can identify where the peaks are and see where the maxima and minima are. If I put the current chart back in, we can watch the current oscillate up and down. And what do you see? Well, you see the current in the inductor in the circuit oscillating again in a different way than the voltage oscillates. For instance, right now we just got past maximum voltage across the inductor. And what do we have? 0 current. And the maximum of the current shows up a little later. So you can go through the mathematics here, but find out that the current lags the voltage by a quarter of a period in an inductor.